Hey class, today we're going to finish up the last section of the respiratory system and we're going to learn about how is it controlled, what regulates our breathing in order to make sure that we're getting enough oxygen inside our body. So here we're going to first talk about neuroregulation, which has to do with our nervous system setting the basic rhythm for our breathing. Two major nerves that affect our breathing or activity of our respiratory muscles are going to be the phrenic and your intercostal nerves. Hopefully you remember from the nervous system that your phrenic nerve is going to affect your diaphragm. And then your intercostal nerves, this is going to affect the muscles around your rib cage. Now, neural centers that control rate and depth, they're going to be located to the medulla and the pons. So often these phrenic and intercostal nerves are going to send impulses to or from the medulla and the pons. Now, in terms of receptors, how do they receive signals in order to tell the body what to do in terms of breathing? Well, bronchioles and alveoli, for example, have something known as stretch receptors, and they respond to make sure that the tissue is not being overinflated when you breathe in. So what happens is if it does reach where it becomes overinflation, could be a possibility, your vagus nerve, which again is part of your autonomic nervous system, is going to send impulses to the medulla to tell you to stop breathing in. You've reached your capacity. Now that we've kind of mentioned that the neural centers of your brain are going to be in the medulla oblongata and your pons, let's look a little bit deeper into those two structures. If we're going to talk about the first structure, your medulla oblongata, the main function of this is to set the basic rhythm of breathing, and they do that through two respiratory centers. The first one, known as the ventral respiratory group, or VRG, is essentially the pacemaker of the breathing system. It controls breathing rhythm by containing inspiratory and expiratory neurons that tell you when to breathe in and when to breathe out. The second one is the dorsal respiratory group, and this contains sensory receptors that help communicate information to your VRG in order to help modify those breathing rhythms that have been set by the VRG. The second major structure in the vein is your pons. This actually helps smooth out your respiratory rate and or transitions during such activities like singing, sleeping, and exercising. I like to bring up this picture, and we're going to bring up this picture here later because I want to show you that two structures in your brain are going to be your pons and your medulla centers. So pons and medulla. Remember, pons and medulla are actually part of your brain stem. So these are both part of your brain stem. These help send out signals down your phrenic and your intercostal nerves. Again, here you see your phrenic nerve go down to your diaphragm. Your intercostal nerves go down to your intercostal muscles, which are located near your ribs. In terms of talking about control of respiration, since the medulla sets the pace, we're going to talk about what counts as a normal respiratory rate and what is not. So a normal respiratory rate, which I'm going to butcher this, is eupnea. This is about 12 to 15 breaths per minute or respirations per minute. That means you have breathed in and breathed out 12 to 15 times. Hyperpnea, this is increased respiratory rate, and usually this occurs because your body needs extra oxygen. For example, when you exercise, you need to be able to breathe in more oxygen for your muscles. Now, it is not mentioned here, but I'm going to go ahead and talk about it because often this is a common homeostatic imbalance found in adults, mostly overweight adults, but other adults as well. There is something known as sleep apnea. So apnea is where you are not having enough breaths per minute, and often you can stop breathing. Sleep apnea, this event occurs while you are sleeping, where you have completely stopped breathing while you are sleeping. This can actually lead to heart disease and different effects on your heart since it will make it work harder, and there is the possibility where you would stop breathing in your sleep and possibly pass away. Now, if we go to non-neural factors that influence respiratory rate, we can look at physical factors, volition activities, so things that you can control, and emotional factors. So physical factors could be things like increasing your body temperature is going to increase your breathing rate. Exercise is going to increase your rate. Talking is going to increase your rate because you're going to have to be able to breathe in while you're also talking and breathing out air. Even coughing. Volition, which are activities under conscious control. Think about to your own volition, your own control. So these are things like singing, swallowing, holding your breath. You can tell yourself to swallow and you can tell yourself to hold your breath. Now, while these are under conscious control, you can hold your breath if you want to. Know that this control is very limited, and actually, if you hold your breath too long, your involuntary nervous system takes over and makes you breathe again or make you gasp for air. So a lot of little kids like to hold their breath to kind of taunt their mom or dad that, hey, I'm going to hold my breath until I pass out, but they're going to actually breathe shortly later because their brain's going to tell them to. And then you have emotional factors such as fear, anger, and excitement. These are obviously going to increase your respiratory rate, especially if you are terrified. You hyperventilate. Other non-neural factors are different chemical levels within your blood or within your respiratory system. The first one we're going to talk about is your CO2 levels, your carbon dioxide levels. Your body wants to get rid of carbon dioxide. It's actually the most important stimulus for breathing. Like I said on the last slide, a lot of little kids love to hold their breath to taunt their parents, but when they hold their breath, carbon dioxide builds up within their bloodstream, it builds up within their respiratory organs, and that actually is what stimulates you to start breathing, not the lack of oxygen. Now, increased levels of carbon dioxide, why does it cause you to start breathing? Well, carbon dioxide, if you remember from how it gets transported around the body, it gets transported around the body and becomes carbonic acid. Now, this this actually leads to, oh my gosh, I don't know why I couldn't read that. I'm sorry. This leads to carbonic acid. This causes a decrease in pH. And if you know anything from pH from chemistry, if you have a low pH value, you're considered acidic, considered carbonic acid. And this acidity builds up in your blood and actually increases your rate and depth of breathing because it wants you to get rid of that carbon dioxide to restore your body back to normal conditions. And it does this by acting directly with your medulla oblongata. In terms of oxygen, changes in oxygen concentration are usually detected by chemoreceptors in your aorta, which is your big, huge artery that's going to leave your heart, and your common carotid artery that leads up to your head and through your neck that splits into your internal and external. Information is sent to the medulla whenever we realize oxygen levels are low, and oxygen is a stimulus for those whose systems have become accustomed to high levels of carbon dioxide as a result to a disease. So instead of the carbon dioxide telling you to breathe, some people develop a disease where it doesn't before you need to, so oxygen is that second stimulus. I bring up this picture again because here we have what happens, well, CO2 and H plus increase in the tissue. And again, that's one thing that stimulates you to breathe. And notice that the arrow is going straight to your medulla because that's what it's going to work with. And then even here, nerve impulses from O2 sensors. This could be from your aorta, so your aortic body, or your aortic arch, or remember from your common carotid as well. Common carotid as well. Other non-neural factors that are chemically related is hyperventilation. Hyperventilation is when you do have these rising levels of CO2 in your blood where you have acidosis or your blood is more acidic. This is going to result in faster, deeper breathing because we want to get rid of those CO2. We want to elevate blood pH and bring it back into its normal range. Now, if you do this too often, for example, people like to just breathe hard for no reason to be silly, this can actually get rid of too much CO2 where you can develop apnea or dizziness, and it can actually lead to the opposite effect, alkalosis. Hypoventilation, hypo meaning too low. This is where we have slow and shallow breathing. It becomes so slow that it allows CO2 to accumulate in the blood. And the reason we hypoventilate is whenever our blood becomes alkaline, which means too high of a pH, we want to be able to lower it so it goes back into our normal range. So that's the end of today's lesson. Let me know if you have any questions, and I'll be more than happy to help. And I hope you guys have a good day.